Bonjour. This is going to be my first lecture in France, possibly ever. I'm sorry I can't see the audience, but I will try to act as if there are people watching me and trying to understand what I'm saying. Superpolynomials are formed with commuting variables, which are called the x's, and fermionic variables, which anti-commute. So there's never a second power, and the x's and the thetas commute. The symmetric group, which is considered as the group of permutations of the set 1 to n, is going to act on the polynomials. The most important permutations are the transpositions Ij and the adjacent transposition, which is called Si, which takes I to I plus 1. The braid relations are, as you can see, the Coxeter relation would be that the product of Si times Si plus 1 is of period 3. The S's commute if the I and J are far apart. The permutations act on polynomials by permuting the variables each. For example, S1, theta 1, theta 2, since it interchanges them, and so because of the skew property, you get a minus sign. S2 and theta 1, theta 3 just takes theta 3 to theta 2. We need a basis for polynomials in theta. They will be indexed by sets. We write them in increasing order. So for a set with m elements, this is the function polynomial phi e. The span of all these polynomials where the cardinality of the set is m is called Pm. The span is over some extension field of Q. We only need one parameter here, Q kappa, or maybe later on Qt. Kappa is generic, so we avoid fractions whose denominator is between 2 and capital N. The bosonic variables are spanned by x alpha, the usual multinomial kind of thing, and SPM will be the span of x alpha times the phi e, where e is cardinality m. On these polynomials, we have the Dunkl operators. The difference here is that theta is interchanged, the theta ij's, and so the x's work. So this is indeed a polynomial. This is the Cherednik operator, which the di's commute among each other, the u's commute among each other. The group acts on di as usual. The action on the u's is more important. This one here, si, ui, si, is ui plus kappa si, is important for computing the polynomials. Since these operators commute and they preserve the degree, they have simultaneous eigenfunctions. They're called non-symmetric Jack polynomials. They're a special case of the generalized Jack polynomials that Stephen Griffith constructed for the complex reflection groups GNPN. Transactions 2010. To start, we need to get the fermionic variables, find out their how the group acts on them irreducibly. First, there's a differentiation operator that just looks like what it does, but you have to take into account the order. So to differentiate with respect to theta 2, you move it to the front, getting a minus sign. D is the sum of the di's, and then d squared is 0. Then there's a multiplier operator, just multiply by the sum of all the variables. And here's an example. There's a theta 2 pops into the middle, giving us a minus sign. The theta 4 is at the back. M squared is 0. M and D commute with the group action, and they have this nice relation. MD plus DM is n, the number of variables. PM0 is the kernel of D intersect PM, and SPM, these are the superpolynomials in that kernel. PM1 is the kernel of M, the multiplier operator, and SM is the corresponding one. So it turns out that the polynomials are a direct sum of the two types 0 and 1. The representations of the symmetric group are indexed by partitions of n. Given the partition, this means non-increasing labels, you form a Fourier's diagram. You have boxes at ij, where I is less than the length, the number that's the number of non-zero entries, and j is between 1 and lambda I. I use reverse standard Young tableau. This comes from the choice of the Cherednik operators starting from the front. So you put the numbers 1 to n into the Fourier's diagram, that the entries in each row and each column are decreasing. And then the action of the symmetric group, this is only a superficial part. If I and I plus 1 are in the same row, then SIY is y. If they're in the same column, you get a minus y. The important idea of a content, if k is in the cell ij, the content is j minus I. So the column label minus the row label. The content vector actually determines the Young tableau. This sort of starts from the back. The uses Murphy elements. So omega n is 0, and then you sort of work your way down. And the whole thing is set up so that the tableau are eigenfunctions for the uses Murphy elements. And the eigenvalues are the contents. If you find an if you ever find an eigenvector of the omega i's, you look at the eigenvalues. The eigenvalues give you a content vector, which determines the shape of the partition. And so that will already take care of that. Here's an example. Let's take n5, m equal 2. Take the set 3, 4, 5. Differentiate. You get that. You can verify directly that it's an eigenfunction of omega I. These are the eigenvalues. That's a content vector of this tableau. So 2 is here. This is 1, 2, then minus 2, minus 1, and 0. And the representation is called 3, 1, 1. It's degree 6. It's degree 6 because you have 4 choose 2 numbers you can put into the column. This is called the hook tableau. In general, we take the tableau, which has the n minus 1 going down the column and remaining numbers in the row. So that's called E0. You can figure out that the eigenvalues correspond to this tableau. I decided that it uses up so much space going down the column, so I've invented or whatever, settled on this thing. This is the first row, and then the first column takes a little dip and comes down here. So that is actually the column. So the isotype is n minus m, and then 1 repeated m times. The analysis of PM1 is similar, and we won't talk about it here. And it's at the top. Here's how you construct the basis. You start with, you order it by the inversion count. The inversion count is the number of pairs where I is in the first one and j is in the second, but I is less than j. So E0 has inversion count 0. And the maximum is if the biggest numbers are in the top row. Then you can construct elements in PM0, which are eigenfunctions for the uses Murphy elements. And so they're the derivative of phi e, and then a sum over sets with lower inversion count. So you induct on the inversion count. And this is a typical formula to go from, you move one element from the first column into the row, and then this is how the standard formula produces it. And they have the right properties with respect to the action of SI. Here's an example. N is 5, M is 2. So this is the set 3, 4, 5, 2, 4, 5, 1, 4, 5, but they're not all there, 1, 2, 5. So for example, let's look at this one, 4, 5. So if you switch 4 and 5, this gives you minus sign, and this gives you minus sign because you reverse the order for these variables. There are, the dimension, as I said, is 4 choose 2. There's a nice way of counting the inversion. If you take this generating function, q to the inv e, you get the q binomial coefficient. And so this tells you how many sets there are of each inversion count. To get the eigenfunctions, we need to put an order on the variables. This is the usual dominance order, and this is that's just for usually say partitions. And then this is the derived order that alpha is whatever less than beta. If either the alpha plus, this is the non-increasing rearrangement. In other words, you make a partition out of the elements. If that's true, or they have alpha and beta are permutations of each other, and alpha is less than beta. There's a rank function. So if a partition will have a rank function of identity, otherwise it's something else. It's always a R alpha is always a permutation. Here's an example. Alpha is 4504. That's the rank function. And if you act with the rank function on alpha, you put it into a non-increasing order. Then this is the expression of the simultaneous eigenfunction corresponding to an index and a set. It's x alpha. You have to act on tau e with the rank function inverse. And then there is a bunch of other things where beta is dominated by alpha. And the coefficients are rational in kappa. And this is R alpha, remember, is tau e inside. They said this is the spectral vector. If you act on them by the Cherednik elements, you get the eigenvalues zeta alpha I plus 1. You put the rank function into the tableau, read off the content, and that gives you the eigenvalue. Here's an example. I have to use very low degree because they just blow up and they won't fit on any screen. So alpha is just 1, 1, 0. There's a set. There's the rank function. These are the eigenvalues, 1 minus 2 plus. But the thing to notice is that you get different signs. In scalar value Jack polynomials, you're just going to get pluses. I mean, kappa will show up A plus kappa B. Because this is different, we can get both negative and positive. And so here's the x2 minus x3. This is its coefficient, and then here's the other stuff. And once again, notice that we have both positive and negative poles in terms of kappa. We would like an inner product on these polynomials. It should be invariant under permutation. And this is the contravariant property, xif. If you move it to the other side, you differentiate. So this takes care of shifting degrees. And we declare that different degree homogeneous polynomials are orthogonal. And you'll write norm f squared is ff. It doesn't say it's a positive inner product in general. The lowest degree, we make phi e to be an orthonormal set. And again, working more or less with the adjacent transpositions, we get this formula for the L2 norm of tau e. There's the similar relation for the Jack polynomials. So this gives you a formula for going from alpha to Si alpha in the downward. So you're moving the large entries to the left. Your orthogonality of the two allows us to get a formula which relates J alpha to J alpha plus its non-increasing rearrangement. And so one gets this gigantic product over all pairs which are out of order, and it uses the contents. That's inside 1 degree. To go from 1 degree to another, there's the affine step. This is how you create a larger degree polynomial. You shift the variables with Wn, this big shift, and then multiply. And this leads us to this formula. So this is a product of using the contents, and then we have more content formulas. And then the relation is the J lambda, the norm of J lambda is the norm of the tau E part in this polynomial. This inner product, this formula is a special case of the formulas that Griffith found for the complex reflection groups. The product is positive for kappa between plus and minus between 1/n. Here's an example for n equal 4. It's sort of, at least it illustrates that the norm, as you see, has both positive and negative poles and zeros for kappa. I'd like to move on to the Macdonald polynomials, which is based on representations of the Hecke algebra. The Hecke algebra starts like the symmetric group, that we have the elements Si. We keep their braid relations, but we put in a new quadratic relation. So TIs are abstract generators. Lowercase t is a parameter which is not an nth root. For small n, for 2 less than capital little n less than big N. Here are the braid relations, and here's the quadratic relation. We'll take some extension field of the rational Q and T. So we can form the group algebra of Sn with this field. And the Hecke algebra, there's a linear isomorphism between the two. What you do is, given the permutation, you write it in the shortest form as a product of adjacent transpositions. The number of terms is more or less the number of inversions. And then Tu is the product of the corresponding T's. If there are different products, the braid relations say that you get the same result. The representation theory has the same ideas as the symmetric group. Now, how does the Hecke algebra act on the superpolynomials? First off, just on the theta variables. This is really enough to define it. Theta 1 goes to theta 2. Theta 2 goes to t theta 1 plus t minus 1 theta 2. So that's the difference right there. You see, if t is 1, you just get the symmetric group back. And t1, and on the product, it reverses them, just like the transpositions. For example, this is invariant. Theta 1 plus theta 2 is just multiplied by t. Here, an example, t2 of theta 1, 2, 4 is this, and 1, 3, 4 is that. We need irreducible modules. So same is the same, the multiplier. The derivative operator has a factor of t in it. The m and d commute with the t's. M squared is 0, d squared is 0. md plus dm is whatever you call it, the t number of n or something. One minus, very familiar, 1 minus t. We use the same notation for PM0, PM1. They're irreducible modules. The Eustace-Murphy elements look quite different. You start with ti, go up to tn minus 1, go to t minus 1, go back to ti. If you, of course, you see that if you replace these things with si's, you just get 1 here. So these things disappear when t is 1. Omega n is 1, and then we have that. The Hecke algebra is represented in such a way that omega I acting on the tableau is t to the content of I. Here's the illustration, sort of the same as before. N5, 2, tau E is the derivative of this. So now we see we get powers of t. The eigenvalues, t squared, t minus 2, t minus 1, 1. So if you read off the 2, 1, minus 2, minus 1, 1, you get the content vector of this tableau we had before. In general, we do the same thing. We take the set E0, which has the biggest numbers in the first column. The eigenvalues correspond to the t, I call it t exponential. So it's t to the contents of the same thing we had before. It's again, the degree is n minus 1, choose m. And if you act on the tau E with TIs, you get a submodule. I used this concept before. Now here's an example. How do you get the content of a set? You take the set E, you put it in the first column, right? So this is the first column, 8752. You take the other numbers and put them in the first row, read off the contents. 4, -3, 3, 2, -2, 1, -1, 0. So that's the content vector of E. Again, there are basis elements generated essentially analogous to the symmetric group. You arguing over the inversion count. This time, the adjacency relation involves the contents and t's. If you sort of look at it and let t go to 1, you should get the same thing as we had before. I need these functions u0, u1. They show up over and over again. And uz is the product of them. They're used in formulas to make formulas shorter. Here are some basis elements for the same set I had before. Notice the t shows up in various ways. And here, instead of 1/3, we get the t number of 3 and so on. So t shows up in various interesting ways. Now we'd like an inner product on the basis sets, the phi-e's. I want the operators ti to be self-adjoint, and then the omega i's will be self-adjoint, and the tau e's will be mutually orthogonal. The correct definition is phi-e, the inner product of phi-e, phi-f is t to the minus inversion number of e anachronic of delta. Extended, this does satisfy the self-adjoint property, and we can work out a formula for the norm, the squared norm of any tau e. So this is why I needed this function u. There's u0 and u1, and you need both of them to make this work. This is the key point. How do you work on how do you let the Hecke algebra act on superpolynomials? So this is the de Mazur operator. And so first, this is just the polynomial, let's say the scalar case. And then this is the trick to make it work for modules. You act by ti on the theta variables. Then we need something like the shift. Let's call it tn. So this is a product of the t's in this order. One more parameter q. Then we have the action of w. So the x's are shifted, multiplied by q. And then the tn shifts the theta variables. You put it all together into xi. Let me just emphasize that I'm using a very bold-faced t for the superpolynomials and x and theta, and the regular t for just theta. So notice that these are bold-faced t's. This is a Cherednik operator from his 1995 paper, and also Baker Forrester discussed these in their 1997 paper. These xi-i's commute. So there is a basis of simultaneous eigenvectors of xi. These are the non-symmetric Macdonald superpolynomials. Jean, Gabriel, Luc, and I worked out this theory for modules and not just the scalar case to prove that you have to prove that the relations work, the braid relations and so forth and so on do what they're supposed to. When you restrict bold-faced t to regular t on a polynomial in theta by itself, xi coincides with the Eustace-Murphy operator. Next, to get an expression for the superpolynomial, the eigenfunctions, you need something that corresponds to the rank function. So if R alpha is this product of S's, then TR alpha is this product, same order. So given a label and a set, there's a xi simultaneous eigenfunction. It has some this sort of nuisance powers of t and q. You have to chase them around through the various steps. There's the labels for the exponents down at the bottom. The important part is x alpha and then R alpha acting on the tau e. And then there's the stuff where over multinomials dominated by alpha. These coefficients are rational functions of q and t. The eigenfunctions the eigenvalues are q to the alpha I, so that's easy, and then t to this content thing. So to work with norms or construction of these, we use the Yang-Baxter graph technique of Lascaux, that you put the nodes labeled by the multi-index in the set, and then you have directed edges, which should give you the direction of the construction. The start is at the bottom, M alpha E, so this just depends on the set. If alpha I, so we argue somehow with the largest index on the right side, put Z, the ratio of the eigenvectors, the eigenvalues, pardon me, and then that is the formula for S. E is the same, and alpha, we've moved the alpha I, interchanged these two values. If there are alpha I and alpha I plus 1 are equal, then you find the rank of I, the rank function of alpha at I, excuse me, so you get some other number. If this pair, JJ plus 1, is partly in E and partly outside of E, then in this order too, then there's a transformation formula which moves you from E to E with J and J plus 1 interchanged. If J and J plus 1 are in the same column, then you just, it's M alpha is an eigenfunction with -1. If JJ plus 1 are in the same row, then the eigenvalue is T. To change degrees, there's the affine step. Again, it's phi alpha, puts alpha 1 at the back, adds 1. The recipe is add x by W, multiplied by xn. The E stays the same, and alpha is transformed. The spectral vector, it's shifted over, and this one is multiplied by Q. The proofs depend on a bunch of commutation rules. Too complicated to prove here. Here's an example of what one of these polynomials looks like. Again, I had made it very simple because they get too big to put on a screen. So alpha is just one miserable little x. So here's x3, and here's some data stuff, x4 and x5. And this is the interesting part. Notice that there is a pole at q equal to t minus 3. So the poles are always interesting in these formulas. It's where things go bad somehow. This is the spectral vector. And M alpha has this property. You can interchange, because 0 and 0 are adjacent. In the column, you get a minus sign. Now we have the inner product. Well, the Jack polynomials have a, remember, had this property xifg is fdig. Well, you can't do that. What is the analog of di? This is from Baker and Forrester. This is the definition of dn, so it's a derivative. It lowers the degree by 1. And then to get the other derivatives, let's call them, you shift left, multiply left and right by ti, so it's an inductive definition. They do actually map polynomials to lower degree. Here's sort of a proof depending on the existence of the Macdonald polynomials. If alpha n is 0, then the rank, this content, the rank is n, it sits in the top box, the content is 0, so the eigenvalue is 1 and it disappears. If alpha n is greater than or equal to 1, then use the affine step to show that dn m alpha e is a transform of w m beta e, where because alpha is whatever, it's sort of shifted in the other way. The d's commute. Here are axioms for the inner product. TIFG is FTIG. I want it to be self-adjoint, and I want xi(n) to be self-adjoint. From those two, we can get all the other operators, Cherednik operators, self-adjoint, so we get orthogonality of the eigenfunctions. This allows us to relate this hypothetical, I should say, these are hypothetical formulas. I haven't proved it exists, but if there was such a norm, it would have to look like this. We have a product similar to what was set up before for the Jack polynomials. Then we need one more axiom. You can't use the one from Jack polynomials. It does not work. You just can't get it to go. So this is what it looks weird. So there's a W inverse over here. So there's a raising on this side and a differentiation over here, but it has to be tinkered with just a little to make it go. The 1 minus Q works so that you can take limits. Then we need degree raising operation. Again, we use the affine operation. You work through the derivative, use the properties we've set up before to find out that this relationship holds. So this formula allows us to go up by 1 degree. Having got these hypothetical formulas, we try to get something for every m lambda e. This is just a sketch of how you do it. So take the last non-zero entry of a partition label. Call it lambda k minus 1. Now move it to the front with the adjacent things. Notice that there actually is the backward. Before it took larger things to the front. Here I'm taking the smallest thing to the front, but there are formulas for that. And having gotten it here, I use the affine step to put it here, add 1, and now we use once more the various steps to move this to lambda. And by using the adjacency relations, we get a formula for. And there it is, gigantic formulas, gigantic products. These are the good old Q-shifted factorials. And having got this formula from hypothetical arguments, one has to show that what we did was correct, so that every way of getting to something gives you the same answer. Otherwise, it wouldn't show that we've satisfied every axiom. But of course, that's part of the work that's in there. If Q is positive, then and T is bounded in this interval, then it's an actual positive definite norm. Here's sort of one side trip. Can we find special values? Ordinary polynomials, whatever, do have special values. Here we sort of restricted. If I take the set that has the lowest numbers in the first column and take lambda I, so it's 0 for I greater than m. Here is the special point, the downward powers of t. Then we can actually evaluate the Macdonald polynomial. We get hook products. We get the shifted factorials. These correspond to the lambda, whatever, the generalized Q Pochhammer symbol corresponding to partitions. Q minus n. Without the, in general, if you didn't have this, you would these would disappear. And this is a hook product. Because I've used this one, I'm getting p minus 1. There's an analogous one where you put the lowest number in the first row. This is the definition of a hook product. I'm sure you've all seen it. And then there's some exponents for it. And I think that there is no nice evaluation formula for arbitrary E and alpha. Lambda could be, there is one if you change lambda to alpha, you just change the hook product. But the situation of this special set, I think, can't be pushed. I mean, not a nice product formula. I have a few minutes left. What can we do in terms of symmetric? I'll get to what symmetric. What module is generated by one polynomial? So if you start with 1 and beta f, what can you get to by using adjacency relations? It's easy to explain. Given the set E and a label, form a tableau, alpha E. You replace I by alpha I plus. And here's an example down below. Here's a set, 2, 3, 6, 8, 9. Here's a label, order alpha. This is the order. Then you write alpha into the tableau according to the content vector over here. So this is the thing called alpha E. That determines the module spanned by M alpha E. so that to know if beta alpha has the same tableau, then it's in the same module. In this module, is there a symmetric element? Symmetric means big TIP is TP. It's not the same as SN symmetry. The eigenvalue is T and not 1, but the word symmetric seems to be, I don't know what else to call it. Luke and I proved that if alpha E is column strict, the entries in column 1 are increasing. There's a unique non-zero symmetric P. Otherwise, there is none. We use the methods of Eigenfunctions. I'd like to point out now that this group, Blondeau, Fournier, Desrosiers, Lapointe, and Mathieu, did do Macdonald Superpolynomials. They're conceptually different. But one of the things they define, a superpartition, is totally relevant here. A superpartition is an n-tuple. The first lambdas are strictly decreasing. The second batch is just non-increasing. So in our example, the superpartition is 65326, 2 semicolon, these strictly decreasing. In general, the isotype for n minus m, 1m, the numbers lambda 1 through lambda n are in column 1 of this tableau alpha E. It's so that lambda capital N is less than lambda m. The other case, by the way, the lambda n greater than equal would fall under the thing I'm not talking about, PM1. The number of tableaux of this shape is has an easy generating function. Here it is, with the coefficient of Q. How can we find the symmetric polynomial? Well, it's a linear combination of all the betas. You apply this equation. The space breaks up into one-dimensional and two-dimensional modules. So, because there's only these two eigenvalues in one. So, we just find coefficient. We find relations for adjacent coefficients. There could be different sets as well. So you have to, there are two different sets. ER, the root minimizes the entries in the first row and the sink maximizes them. So for our previous example, this is the original one is the root and the sink. And so once again, more formulas. Let's move straight forward. This is the result. So that C0 product that involves contents, the R0 involved the eigenvalues. This is unique with normalizing the coefficient of m lambda ES. Here's an example of what one looks like. So remember, symmetric means that capital TIP is little t. It's not symmetric in the group sense. So it's more or less screwed up here, as you can see. It's not symmetric in the group sense. For a bigger label, 210, I can't write it all here. Here's what some of the things look like. X1 squared, X2. This one is sort of interesting that in the Jack case, this wouldn't show up because you notice we put t equal to 1, everything disappears. How can we symmetrize? Given a polynomial, how do you make a symmetric one out of it? You act on it by this cute little operator. X0 is 1, and then you sort of multiply again and again and again, multiply them out. The nice thing about this, I point out for people who like to use Maple to find stuff, is that it's easy to implement. You don't have to make a list of all permutations to make it work. It just iteratively produces all the permutations you want. It's self-adjoint because the idea is that, in fact, this thing I called Sn is the sum over all permutations of Tu, and it's self-adjoint. So then if we take anything alpha f, which is in the orbit there of lambda e, the symmetrization of it must be multiple of that one thing we're looking for. So we can actually find the norm with some clever trickery here that think this is the Baker-Forrester trick I'd like to add. So we have different ways of computing this inner product. On the one hand, it's some constant times that, factorial. If you take the right alpha, yeah, you can compute the coefficient, and we get some, these are multiplicities of the number I in row 1 from 0 on upward. And so we get sort of a multiplicity, and then we get this one here. And with some computation, you can get this gigantic thing here. Let me just recall here that Stephen Griffith's observation in his original paper was that these formulas are so gigantic because there's no nice cancellation. In the scalar case, there are adjacency relations for these contents because they only differ by 1 from one number to the next. And so there's cancellation like crazy. But in this, in general, it just doesn't happen. And so we have, I can't even count how many terms there are in this product, but there it is a closed formula. And that is the end. Thank you.
So thank you, Charles, for your talk. So we have time for some questions, maybe first from the audience in Lumini. Yeah.
Hi, Charles. Good to see you again.
Hello.
So yeah, I wonder.
I'm happy to finally see you.
Yeah. So I wonder, have you thought about trying to work out a theory, not where the t's and x's are self-adjoint, but where they're unitary? Like where the adjoint of ti is ti inverse in the qt case?
Well, in my paper with John Gabriel, the inner product was actually not an honest inner product, but one side you had to use T inverse and Q inverse.
Right.
And that
right.
works.
Yeah. Oh, okay. Yeah. So right where the where Q goes, where it's sort of
maybe
linear
that's for the
QT.
complex case.
Yeah. That's right. Okay. Thanks.
So are there further questions or remarks from here, from the audience? No, then I would take a look at our remote audience. You may just raise your hand in the reaction. So at the moment, or just start talking. I do not see any questions here. Is it possible?
Now, may I make another comment?
Yeah, sure.
Since I have a minute. There are open problems, what I'm talking about, and certainly one thing is the finding singular polynomials. These would be polynomials which where their eigenfunctions, excuse me, they have the same eigenvalues for the Eustace-Murphy elements as for the Chrednik operators. And they're sort of interesting in terms of finding mappings between modules of the Hecke algebra, or between what should be called the standard modules. And I think that's an interesting, there are interesting problems connected with that.
So, I mean, one almost trivial question is, of course, whether these super Macdonald polynomials have applications in physics, quantum theory, or some conformal field theory, or can you?
I've not been able to think of a connection at this point.
Oh, now we have a problem with the it's fading away. So
I think that was a double image.
Yeah, so you were just fading away in a certain sense. So looking again for any further questions. But not. I don't see any. Yeah, Eric?
So thanks, Charles. Nice to see you. Is there
Eric,
some
yes.
obvious super Hecke algebra around which you can maybe define at a purely algebraic level, which is related to these super polynomials?
Wouldn't you have to start with finding a super permutation somehow? I mean, do it first for the symmetric group?
Yeah, well, maybe it's a fake question. I don't actually really understand it myself, but like you have super Lie algebras and so on, do you also have super Hecke algebra in general set?
I wouldn't be surprised. I haven't looked into that.
Maybe you should use this. Okay, yeah.
So I just mentioned that maybe the spin symmetric group is the correct
Yeah.
place to start.
Oh, so you need
along
the
the
Hecke
lines of
algebra of the spin symmetric group,
yeah, something like that.
or type Bn, maybe the Bn group.
I suppose. I mean, that's another possibility, of course.
Yeah.
Okay, so let's thank Charles again.
Thank you.